Welcome to the Distinguished Lecture series and our talk with Cynthia Dwork. In a moment, I'm going to introduce our faculty director, Emmanuel Candice. My name is Chris Menzel. I'm the executive director of Stanford Data Science. Who here has heard of Stanford Data Science before? Some of you, most of you, okay, that's good. Stanford Data Science is an initiative on campus to bring together data science practitioners, those using data science, those creating new techniques to understand and learn from data together across disciplines. We're part of the Dean of Research, so we don't sit in any one school, but we try to interconnect all the wonderful data science and machine learning that's happening on campus and how that is applied for new discoveries. This is a distinguished lecture. It's a part of our series of distinguished lectures that we have every quarter. And in May, we'll have our annual conference, so some things to look forward to. If you're interested in this kind of activity, this kind of event, please sign up for our mailing list and you can learn all about it. We don't send too much. And we also have a website at datascience.stanford.edu. So without further ado, I'm going to introduce our faculty director, Professor Emmanuel Candice.
So maybe I'll say two quick things. First of all is that when we planned this distinguished lecture series, I remember sitting with a bunch of faculty members and we had to think of names, and everybody said Cynthia Dwork. That's what I remember. And we're very lucky to welcome you to Stanford and to Stanford Data Science. You're the Gordon McKay Professor of Computer Science at Harvard. And I think not only this, but you're an affiliated professor in the Harvard Law School, which is very unusual. So CS plus law, it's very unusual. And prior to joining Harvard, Cynthia had a very long and distinguished career in industry, most notably at IBM and Microsoft. I think what's remarkable about Cynthia is if I go to the CS department and I say, who is Cynthia? Everybody knows her. What has she done? Everybody can tell me what she has done. And she has done two things especially that are very important. One is she's the co-inventor of the proof of work. The proof of work is basically a form of cryptographic proof where a party, the prover, proves to another party that he or she has done expended computational time to achieve a task. And that's been very important to deter a denial of service attacks. It's been to prevent spam. And for example, Bitcoin has used proof of work extensively. She's also well known, so she has a double win for differential privacy. And differential privacy is extremely important these days. That's why we're also very happy to have you. It's a constraint on the algorithm that you can use to publish statistics about a database in such a way that the amount of private information you release about individual is controlled. And so this is extremely important. So if I have a database of genotypes, I would not perhaps want to have my genotypes published. And so how do you query a database without revealing too much about your genetic information? And she has done pioneering work about this. And these two things are very cool because they're like intellectually very sophisticated, but they're very practical. And so, for example, differential privacy is used by the Census Bureau, it's used by Apple, it's used by Google. So it's a very impressive achievement. So not surprisingly, she has won many awards. She's a member of the National Academy of Sciences, National Academy of Engineering. She has received the ACM Gödel Award, an award I like a lot, named after our own Donald Knuth, the Donald Knuth Award. So that is very important, and the IEEE Hamming Medal. Recently, I got to know Cynthia a bit personally. We traveled to India together to go to a wedding, and so I got to know her a bit. I also know that she's a fantastic mentor, and she cares a lot about young researchers. And so we're very happy to have you.
Thank you for inviting me. Thank you for a very gracious introduction. I knew that it would be fun to be here, but I didn't realize what a sense of homecoming it would be, that I've lived many years in the Bay Area, and I have friends here. I have the parents of my daughter's elementary school friends here, and it's a very, very nice feeling to be back. You don't have to read my handwriting, but when I was thinking about this talk, Some of you may have noticed that the abstract actually really only went up maybe a day or two ago. When I was thinking about this talk, there were many, many things that were interconnected, and many of them I was very excited about, and there have been new developments in them. And I just was trying to figure out what, it's like packing for a trip. You know, what are you going to put in the suitcase? And I drew this picture just to remind myself of various problems and problem areas that we thought about and that contributed and built on each other. And this actually gives an approximate flow of some of the concepts. So it all started with an interest in algorithmic fairness, but there was some complexity theory that affected some of the work. There was a question after a while about what do these probabilities of something happening actually mean? What's the meaning of probability? So there was philosophy of probability and so on and so forth. And this is kind of the path that I want to take. So we're going to start with fairness. And every now and then I'll show you this map and you'll be able to see where we've gotten to. So the study of the theory of algorithmic fairness was launched in the summer of 2010 at Microsoft's Silicon Valley Research Lab. And as usual in good theory, we started by trying to write down some definitions of what does it mean for an algorithm to be fair. And basically, if you don't know what it is you're trying to do, it's very hard to actually do it. So we found that definitions sort of split into two categories. There were group notions of fairness, and what we came up with was something called individual fairness. Of course, we came up with it, so did Aristotle, but you'll see that in a while. So here's some examples of group fairness definitions. Statistical parity. So let's say you're classifying people, yes or no, admit, reject, give the loan, don't give the loan. The statistical parity simply says that the demographics of the accepted group would be the same as the demographics of the overall population. Another is balance for let's say the positive class. So suppose you are assigning scores to people. Our scores are always going to be between 0 and 1. And suppose you have two disjoint groups, A and B, of individuals, and you have true positives in group A and true positives in group B. So balance for the positive class would say that the average score for a positive member of group A is equal to the average score for the positive members of group B. And another notion, which is going to be motivating and important, is within group calibration. So what does within group calibration mean? First of all, let's talk about what calibration means. So you have a scoring function that is assigning a score or a probability to individuals. So you can think of this as predicting what are the chances of rain. Each day you predict the chance of rain for the next day. And your predictions are calibrated if for every value v between 0 and 1, say 70%, if you look at all of the days on which you have predicted v, then in fact on a v fraction of them, it should rain. And calibration, within group calibration requires that scores are calibrated, if you have different demographic groups, that they're calibrated not just for the population as a whole, but the scores for A are calibrated if you only look at the scores for A, the scores for B are calibrated if you only look at the scores for B, and so on and so forth. Now, calibration has been studied in the forecasting literature for at least 4 decades, dating back to the work of Philip David. And it's kind of viewed as the sine qua non of forecasting. And lots of variants of it exist, and we'll touch on that later. But as a fairness condition, the two disjoint group calibration requirement was proposed as a fairness condition for algorithms, fairness desideratum, by Kleinberg, Mullainathan, and Raghavan. We, in our early work, felt that group fairness notions really sort of fall down under scrutiny. So Suppose you are advertising your steakhouse, and there's group A and there's group B, and you're supposed to advertise equally with statistical parity for the different groups. But you really don't like the members of B, so what do? You find out who are the vegetarians in B, and you send the steakhouse ads to them, and you find out who the meat eaters are in A, and you send the steakhouse ads to them. And so you're really only going to be drawing your clientele from group A. So something is amiss with this notion. You might have very different distributions on individuals, and your statistical parity behavior might somehow reward members of minority groups that look like or act like or dress like members of the majority. It's also surprisingly hard to test for some group fairness notions. And research from the Journal of Criminology, the Annals of Criminology by Neal and Winship talks about some specific examples where you have benchmarking problems, which is a statistical notion of fairness. And they give examples where you would have to know what the police are thinking in order to figure out whether the behavior was discriminatory or not, that the numbers themselves were not sufficient. And then came the famous compass story, and if you don't know the details of that, we'll just look it up. But what was really going on, the heart of that, as was observed both by Chuldachova and Kleinberg, Mullainathan, and Raghavan, is that certain very natural, desirable conditions, small numbers of them, could not be satisfied simultaneously by any scoring function or any classifier. And so you have these group notions of fairness, and you want all of them, and you can't have all of them simultaneously. And I think that, looking and saying, oh, well, maybe we have to choose two and we can't have the third, I think this is completely the wrong way of looking at it. Maybe you don't want any of them. Maybe you want some amalgam. Maybe you want some other property. Okay. And finally, if you are going to think about groups, which groups? Which groups should you be considering? And what about, intersectionality? How do you want to deal with that? So it's problematic. Okay. Now, an alternative is what we called individual fairness. And individual fairness says, suppose you're trying to, let's say, build a classifier for a particular task T. Maybe it's deciding who should get an advertisement. Maybe it's deciding who should be jailed. Maybe it's deciding who should get a loan. Okay, but there's a specific task in mind. Then what we would want under individual fairness is that people who are similar with respect to that particular task should be treated similarly by the classifier. So one way of formalizing this is we have a classifier C, it operates on an individual X. Maybe it says yes or no, maybe it gives a probability and you then flip a coin according to that probability and decide what to do. Either way. So here, if we have two individuals, X and Z, what we want is that the distribution on outcomes that's assigned by the classifier to X and the distribution that's assigned to Z should be close if X and Z are close for the purposes of your particular task. So what I have here on the right is the distance for this particular task of X and Z. We want this Lipschitz condition. Okay? So similar people should be treated similarly. Makes a lot of sense. Aristotle also required that dissimilar people should be treated dissimilarly. We are not. We're only going in the one direction. Okay. Now, the concept that people who are similar should be treated similarly has very strong legal foundation. So that's nice. The problem, of course, is where do these distances come from? What is this distance that's specific to the task for X and Z? if you have these distances, there are a lot of things you can do, and you can build nice fair classifiers and so on. How do you get your hands on them? So that kind of stuck for a while, but there was a bunch of work that started 2018, 2019, and there are some nice ideas floating around for getting your hands on distance measures, and I'm not at all, I don't think we've come to the end of the line on this at all. I'm quite optimistic. Yeah, so I think this is a very interesting area, and there has been more work lately. What else did I want to say? Yeah, let's skip that. Okay. What just happened? So we had our problems with group notions. We also have this problem with individual fairness. We have to get our hands on the metric. Two groups of researchers, independently and at the same time, came up with an approach that is sort of between the group and the individual notions. So I'm going to call this the MultiX approach. X is going to be some kind of a statistical or group fairness notion. And the idea here is we're going to consider a possibly large number of arbitrarily intersecting sets. They're going to have to be large enough sets for practical purposes. And the requirement is going to have to apply simultaneously to every set or every pair of sets, whatever the requirement is, in the collection. So maybe it's statistical parity, so both sets within, maybe it's statistical parity, maybe it's equal false positive rates, which requires a pair of sets, and so on. So that's the multi-X. Multi reminds us that it's multiple sets, and X is whatever the condition is. One particular class is called multi-accuracy. So this was in work here at Stanford of Hebert, Johnson, Kim, Reingold, and Rothblum. And so the requirement in this particular case says that for a pre-specified collection C of demographic subgroups of your population, the predictor should be accurate in expectation simultaneously on each of these sets. So if we look at a set and the average score that's assigned to the member of these sets is 70%, then 70% of them in practice should have positive outcomes. So this has to hold for all of the sets in the collection simultaneously. Now, we're going to step back for a minute and talk about complexity theory, because that was one of the other sort of roots in this DAG. A very beautiful and very powerful lemma proved by Trevisan, Tulsiani, and Vadan in 2009. It's called the regularity lemma, and it has the following. It's a complexity theoretic regularity lemma. And it has the following informal statement. Fix some finite domain, X, and consider an arbitrary function, G, mapping individuals to the range 0 to 1. So here's on the upper right is my arbitrary, wild, obnoxious function, G. It can be arbitrarily complex. Now, given a class F of possibly simple functions, the theorem says that you can approximate G by kind of hooking together in a simple way a relatively small number of these functions in F. So what do we mean, though, by approximate? Because G could be really wild, and the functions in F could be really simple. So what do we mean that by approximating? We mean, roughly speaking, that as far as the members of this family F are concerned, there's no difference between them. And so that's expressed formally here. If we look at the correlation of F and G, the wild function, it looks like the correlation between F and H, your relatively simple thing built up of members of F. Okay? And the two terms that are in purple, where it says low complexity, like how many, well, sorry, whatever low complexity is, it is tied to this value epsilon. The smaller epsilon is you need higher complexity. All right. So again, the heart of the regularity lemma says there is a relatively simple way of approximating very complicated functions, but the notion of approximation also depends on how simple your simple functions are. Okay. And as I said, this turns out to be very, very powerful. It has applications in complexity theory, in additive number theory, information theory, graph theory, and in cryptography. Okay. And here's our first kind of new observation for today, which is multi-accuracy is regularity. Formally, you can write this down in a way that the conditions are actually the same. So the TTV theorem was not constructive. It doesn't tell you how to get your hands on it. What Hebert-Johnson and al. Did was actually show you how to do the construction. And they explain, what the sample complexity is and what kind of computation you need to do in order to build the function. But once you build it, it's not very complicated in the sense that this is not very complicated. Okay, sorry. All right. So, but multi-accuracy arose in the fairness world. What's an example of fairness? Well, it was used, for example, by Gorbani, Kim, and Zhou, also here at Stanford, to improve subpopulation accuracy in gender detection. So some of you might have heard about the issue with gender shades, and this was a way of improving. The complexity connection also ends up giving us, through results that are known in complexity for what's called leakage resilience, and cryptography for what's known as leakage resilience, it gives us lower bounds on the complexity also of multi-accurate predictors. Okay. Good. Now, a strengthening of multi-accuracy is multi-calibration. So remember, before we talked about how Kleinberg, Mulanathan, and Raghavan had proposed, this disjoint group calibration, simultaneous calibration for two disjoint groups as a fairness desideratum. Well, here we're doing the same thing, but now for these arbitrarily intersecting sets. And again, the HKRR construction show how to actually build this. Okay, so where have we gotten? I'm afraid to push buttons now. Okay, we talked about fairness. We talked a little bit about how complexity fed in and gave us these things. And now we're going to talk about probabilities, because scoring functions are assigning to individuals a number between 0 and 1, which is often interpreted as a probability of, I'm going to use the word positive outcome, but sometimes you're predicting things that themselves are very negative, like violence or recidivism. So, and we've got these multi-accurate and multi-calibrated scoring functions, and they're giving us these numbers. And of course, long before any of the fairness work, all sorts of things that are happening in machine learning have been giving us numbers that are used to assess risk or predict probabilities of outcomes. So what are just some examples? Well, what's the chance it'll rain tomorrow? What's the chance that X will repay the loan? What's the chance that this tumor will metastasize under this course of treatment? What's the probability that Y will commit a violent crime? What is the probability of a non-repeatable event? So imagine that your data are so rich that for when we take a person and we represent them to the algorithm, we obviously lose some information. But if we capture enough information about them, you won't have any two people being mapped to the same point. So you can't say, well, take all of the, take a sample of points that all, people that all map to the same point and see what fraction of them had positive outcomes. It's not possible. We're giving a number to an individual and nobody else is getting mapped to the way that individual is represented. So now we're talking about non-repeatable events. You can't, like, if you're trying to predict the chance of graduating in 4 years, you can't go to college and rewind and go again and rewind and so on and so forth. So it's not at all clear what these numbers actually mean. If we don't know what they mean, how do we say for an algorithm whether we are doing what we're supposed to do? How do we say what it is we want, even for the ideal algorithm? What should be the goal of an ideal algorithm? And this might be a complete red herring. Certainly Butler-Lamson took me to task for having dwelt on it, but I think it's important. We don't even know, whether randomness exists. I know the physicists probably think it does, but certainly we can't tell just by looking at the kinds of data that we have whether there's true uncertainty or whether in fact everything is determined and we just don't have enough information or enough computing power to know what the outcome is going to be, and so it appears random. And when you throw that in, it's even harder to say what it is that we want from an algorithm that is giving us scores or predictions. So that's what got us thinking about, maybe coming up with a different kind of criterion. So outcome indistinguishability, which is a notion that has its roots in complexity theory, provides some kind of avenue of attack to this definitional problem. So unlike loss minimization, which is kind of the traditional paradigm for supervised learning, outcome indistinguishability frames learning as satisfying a collection of indistinguishability constraints. So when you produce a scoring function, you can think of the scoring function as giving you a model of the world. And so there's real life, which has real life outcomes, individuals that either had positive or negative outcomes, zeros or ones. And then we have this predictive model, 30% probability of a positive outcome. So draw from a Bernoulli distribution with parameter 30% or 70%, whatever. So what we want is that for a class of distinguishers, or which we will draw in a moment, C, for these distinguishers, outcomes drawn from real life, you look at a bunch of those, should be indistinguishable from outcomes drawn according to the predictive model. So you could think of distinguishers as, say, circuits of a certain size, or decision trees of a certain size, or any other kinds of collection of computing devices that you want. And informally, they take as input an individual and an outcome, and they produce as output. You could think of it as a guess. Did this outcome come from real life, or is it from the model that's given by your predictor, your function? And what we want is that these two distributions, when we have real life outcomes on the one hand or modeled outcomes on the other hand, should be indistinguishable by all of your distinguishers in your collection, computationally indistinguishable. And when you look at it that way, you actually come up with a kind of hierarchy of indistinguishability constraints. So at the lowest level, we call it no access outcome indistinguishability. We have an individual and we have an outcome, and that's all the information that's provided. Okay, and the distinguisher is trying to figure out, is this modeled outcome or real life outcome? The next level, we also provide, when we give an individual, we also provide what is the prediction that the model is making for this individual. Okay? So the distinguisher now has more information. It gets the individual, the model's prediction, which is typically a distribution on outcomes, and an actual outcome. So it's a more informed distinguisher. Therefore, it can do better at distinguishing. And interestingly, this first level here turns out to be equivalent, more or less, to multi-accuracy. It wasn't supposed to work out this way. It just happened. And the next level, which we call sample access, turns out to be equivalent to multi-calibration. Then we get into a very different territory. So the next level up in the hierarchy, the distinguisher is allowed to have what we're calling oracle gates, where it says, okay, it figures out, it's studying stuff, it comes up with some J and it says, tell me what the model says for J. What does the model predict for J? And maybe it does some more computing and it comes up with another J and it says, okay, tell me what does the model say for that? Right? And this turns out to be very, very, very different than what you get over here, much more powerful. But this is something that basically is serving a kind of auditing. So when people say, we're going to have risk prediction algorithms to determine whether somebody should be released on bail, you want to be able to ask the algorithm not just about the person in question. You want to be able, as an auditor, to ask about other people or hypothetical people that you would maybe come up with descriptions for and say, what would your model do on that? Okay, and then the top level in the hierarchy, and there is a provable gap between these two. In the top level of the hierarchy, we just give to the distinguisher the code itself. And then, of course, it can do anything of any of the other levels. So this gives us, as I say, a natural hierarchy. So focusing on the second level, we have outcome sample access, outcome indistinguishability, which is, yeah, okay. And we have multi-calibration and their equivalent. And these turn out to be very, very powerful. Like, there are a lot of things that you can do with them. This is a very partial list, some of the things that I'm excited about, and that there's also, and I'm not mentioning it here, all of these things also make sense in the online setting, and there's a lot of work in online prediction algorithms that satisfy these conditions. One of the things that I thought was really amazing is something called an Omnipredictor. Originally built for multi-calibration, and we'll see perhaps an incredibly simple proof of it as we go on now. So although I said that outcome indistinguishability kind of gets away from thinking about loss, people care about ordinary notions of loss, and there are different kinds of losses that people typically want to minimize for different sorts of tasks. I am not an expert on any of that. Don't ask me questions about that. But I know this much, and the examples here are drawn from the Omnipredictor's paper of Gopalan, Kalai, Reingold, Sharan, and Viter. So the general idea when you have multiple loss functions is that you need to train anew in order to in order to optimize your network to minimize a different loss function each time you have a new loss function. The idea in Omni prediction is to train only once and to be able and to define some post-processing functions that can take the output of this one trained predictor and then post-process in order to do minimization for different loss functions. So you only train once. And I am going to try to tell you the proof because there is a very, very simple one. And it only goes on for about 2 or 3 slides, so if you get lost, you can get back on in a moment. So what does the post-processing do? What the model is doing, our predictor does, is it takes an individual and assigns to the individual a distribution over outcomes. I've been calling it a number like 1/3, but what that really means is with probability 1/3, the outcome will be 1, and with probability 2/3, it'll be 0. So So, and if this were the multi-class case, you would have a more complicated distribution. So the post-processing takes a distribution and maps it to a class of actions, and it's a post-processing function for a loss function if for every distribution, the post-processing on that distribution gives us the action that minimizes the expected loss when the outcomes are drawn from that distribution. So the post-processing for V, for the loss of L, is the action that minimizes the expected loss when we draw the outcome according to V. And with that notation, we can say that what the Omnipredictor does is makes the following guarantee. So this is the more formal version. Given a family C of functions that map individual to actions and a collection of loss functions, F, a predictor, is an LC epsilon omnipredictor if for every loss function, the expected value of the loss on the real outcome when we have post-processed the prediction Fi is less than the expected loss for every C applied to I in the collection, plus some little noise here. So again, F sub I is the model distribution on outcomes for individual I. Fi super L minimizes the expected loss in the modeled world, and Omni prediction says that the loss of the minimizer beats the best action function C in your class. So Omni predictors give best in class loss minimization. Oh, and for my proof, I'm going to take epsilon to be 0. So you'll see zeros and you'll see equal signs instead of less than or equal to something plus epsilon because we took these things to be zeros, and those will all be in red. So this is going to be the proof. It's about 6 lines long. First of all, you can think of, and it's honest, I'm telling you this honest with a small change in parameters. You can say that a predictor is, for a collection C, C0 multi-accurate if the following 2 distributions are the same, the same when it's 0. So if I look at C of I and the predicted, an outcome drawn according to the modeled loss, that's in the same as the distribution on C of I and the real outcomes. And then F is 0 calibrated, so I'm sort of renaming calibration and accuracy, is 0 calibrated if given the model and an outcome drawn according to the model, this is the same distribution as the model and the true outcome. So we have a lemma, which is immediate. It says that if F is C0 multi-accurate, then for every loss function and for every action, every C in our class, the expected loss for C when we plug in the modeled outcome, O tilde, is equal to the expected loss when we plug in the true outcome. And that's immediately from the fact that these 2 distributions up here are the same. So the arguments here are the same in distribution. And then if F is 0 calibrated, then for every loss function, the expectation of the loss on the post-processing with the real outcome is the same as the expectation with the loss on the post-processing with a modeled outcome. And that's coming immediately from this statement, because these are the same. So now we can finish our proof. This is what we want to prove. And we have this line. And then because in the modeled world, the post-processing does minimize the expected loss, we have that this quantity is less than that because the post-processing is the best-in-class minimizer. And then finally, this is immediate from our multi-accuracy statement. So that's the entire proof that these tools can easily give us omni-prediction. Okay, that was the only proof in the talk. Okay, so we've made our way through starting at fairness, complexity, philosophy of probability, outcome indistinguishability, omni-prediction 2. Why is this omni-prediction 2? Because the original proof worked from multi-calibration, and we went back and did it from some weaker conditions. One kind of calibration, not multi-calibration and multi-accuracy. Oh, and I should have mentioned that while the proof on this slide is here, very similar ideas were done by Gopalan, Kim, Reingold, and Vider, and they also have a more refined analysis and delve more deeply into. They get more special. They get stronger results for more specialized cases. Okay, and yeah, okay. So finally, we've talked about fairness. And what happened? No. But that was the goal. That was where we started. But everything we've been talking about since we uttered the word fairness at the beginning has been accuracy. And kind of, what is this fairness as accuracy assumption? Why is that the right thing? And is it really fairness as accuracy, or is it like similar unfairness for different groups, or what? But it's still, I just want to sort of challenge the fairness as accuracy. One of the reasons is that there's a kind of, I don't know, a kind of determinism. So I have avoided discussions of like people's probabilities of success. But the literature talks about these things and even calls real-life probabilities nature. And that's not, I don't think that's right. I don't think that's capturing important aspects. So for example, here you have somebody, you have a woman who is working in a news organization. Now the same woman in one organization, a supportive organization, is going to have a higher chance of success at her job than she would at a misogynist workplace, right? It's obvious. So it's not kind of completely inherent in an individual, but there's something going on which is an individual's interaction with the environment. And in cryptography, we assume that all the time. All of our probabilities involve, interactions among agents or environments, and everybody has sources of randomness, and it's all very, very well defined. Here, it's just like, we're not even sure what kind of randomness actually exists. And again, it's not just located in the individual, but there's also the interaction. Also, it's the case that even who we are was not completely determined at birth, perhaps, right? The environment in which you grow, whether the air was clear, what kind of housing you have, what kind of education you get, what your parents' connections are, what kind of healthcare you have access to, whether your community is supportive or not. All of these things affect your chances of a positive outcome. So it might be nice to imagine a different world, a better world, and try to figure out, what does that world look like? What would these probabilities look like? So we imagine that maybe we start with some kind of a utopia, and we have an individual X in this utopia, and in the utopia, everybody is, given enough to eat and helped to reach their full potential. It's utopia. I don't have to go into details. Just imagine it. And what we picture is that there's some kind of a transformation that occurs that takes a person in Utopia with attributes X and deforms them in some way so that they become X prime. And they have a probability of success or a positive outcome in Utopia, and that because of the transformation and also what's going on in the world and their interactions with the world, that gets transformed to a real-life probability of success that could be quite different. And the transformation might destroy information. Okay, so we can't sort of study real life and get our hands on what does Utopia look like. Nonetheless, we might be able to imagine some kind of a transformation that may be operating on pairs of individuals and their predicted, their real-life probabilities of positive outcome gives us a different world that is closer to the ideal. So we're going to call this imagined tau that walks us in the direction of Utopia but doesn't get us there. That gives us a different world, Q star. Okay. So suppose somebody hands you a tau and says, what does this world actually look like? So the question that we looked at was, when can we build a predictor that looks like this better world? So notice that even with all of these tools, when we're looking at the real world, we never get our hands on the true real-life probabilities. We don't even know whether those are always integer or they can be real valued. But we can come up with a world with a predictor that models a world that is indistinguishable to our class of distinguishers from the real world. So we want to do the same thing for this better world. We can't get our hands on probabilities for the better world, just as we can't get our hands on probabilities for the real world. But can we build something that somehow is indistinguishable from that better world? So in real life, when we build our predictors, we have actual data to train a predictor from. We have individuals and their real-life outcomes. We have no samples from the better world. It doesn't exist. So we don't have the training data. Can we then still come up with something that looks like this better world? And the answer is, well, we have a complete characterization of the transformations for which we can build predictors that are outcome indistinguishable from the better world. And it's a very technical condition, which I can't really, we don't have time to go into. It's called stability under random instantiations. But I will comment that if there is no randomness, then we can definitely do it. Like the condition, this stability under random instantiations is true trivially. And we can imagine the better world, but we can also do it sometimes when, even if the world is not deterministic. And that completes our path through the graph, ending at better worlds. Thank you.
Thank you for the nice talk. The way that you described output indistinguishability was parameterized in two ways. In terms of the data that the distinguishers have access to, and you walked us through how accessing different kinds of data gives different definitions. But you also mentioned that you can parameterize it in terms of the computational resources of the distinguisher, thinking of these as bounded circuits. And I found the latter a little bit surprising, and I was wondering if you could give some intuition for why computational resources should play an important role in that definition.
Oh, great question. Why should computational resources play an important role? In some sense, they don't. I was using those as examples, and I don't care whether, thank you for raising this point, I don't care what these things are. It turns out in practice, you will have to, when you build your predictor, you will be using elements from C. You're cobbling together a predictor using elements of C, so it will affect the complexity of your predictor. And also, an agnostic learning problem for the collection C is also an issue. So like the results tend to dwell on sample complexity. But this is an excellent point, and your intuition is right.
Hi, thank you so much. That was super interesting. It was totally inspiring when you just said the utopia and the transformation. And I'm wondering if you could qualify what a better world would be and how to find those tau options. Because would you look at example data sets where, okay, there was inequality, and does it tie back to notions of fairness that you talked about at the beginning? Thank you.
So I don't want to answer that question. What I would like you to do is think about what you would think would be a better world, and then see whether there is a transformation that would get us there and whether it could satisfy our conditions.
Hello, thank you so much for the talk. My question is somewhat in line with what was just asked. Is in the last slide you mentioned the U star and the Q star, U star being the utopia and then Q star being where we actually end up because of tau. Is there a relationship between the U star and Q star, and how do we like minimize that so we actually get to the utopia that we envision, or is that irrelevant?
I don't have an answer. I mean, we didn't look at that. I don't have an answer to that question. But I mean, the question again is there a relationship between Q star and utopia? All I was hoping for was that Q star is somehow closer to utopia than real life as we know it, than the current real world. Yeah.
Hi, thank you for the talk. You were talking about predicting probability distributions and not being able to validate them because experiments are not repeatable. But before that, you talked about this calibration notion where, if 80% of the events that are labeled 80% should have a positive outcome. It seems that's maybe one natural way of testing whether your probability outputs are valid. And
it is one way, and then there's a very big literature. So think about forecasting. There's a very big literature in the statistics community about forecasting, and you've mentioned calibration, and I said that that was talked about by Philip David in 1982. There are arguments about problems with calibration. Then also in the literature, there's something which basically boils down to multi-calibration, like, well, yes, we want to be calibrated on all of the days, but we also want to be calibrated if we only look at all the even days, and if we only look at all the odd days, and if we only look at all the days where it has rained for the past 40 days and 40 nights, and so on and so forth. And then there's a very general result by Sandroni that says essentially fix any test in advance. And if we know what the test is, we can always build a predictor that will satisfy the test. But on the other hand, there's an argument that you can do all of these things even if you don't understand the thing that you're predicting at all. And I actually have not yet reconciled these two kinds of results. But so anyway, what you're describing fits into this context, but we can think more richly.
Hi, thank you so much for your talk. I had a question about getting these sets of ideas into practice. So as you know, that the industry is quite satisfied with the financial outcomes that it receives by relatively sloppy algorithms that are out there in the wild that don't involve all of this sophisticated thinking. And the regulators are somewhat caught up in the original definitions of fairness. Some of them have reached the level of subgroup calibration, what you call within group calibration, but they're not further along. So how do you see the incentive structures in society getting to these conclusions? Like, do you see regulators coming all the way down to the utopian framework that you shared, or do you see there being a collinearity between financial incentives and getting down to better worlds? Like, how do you see this playing out in the real world from your perspective?
Okay. One of the things that I had on the slide and I didn't mention was use of these things in predicting, I think, osteoporosis and some kind of heart disease maybe. So being deployed by Clalit, which is the largest healthcare provider in Israel. So I have no idea about, I haven't thought about the financial sector at all, but what I expect will happen is there will be, over time, there will be implementations, and they will be found, some of them hopefully will be found to be very helpful, and that things will develop sort of naturally as the ideas are tested further and further. So I can't see down all the way. And I don't really expect anybody to be thinking about better worlds for a long time. I mean, I want to think about it. I don't imagine regulators will for a while. But incrementally into practice is what I think will happen. Yeah.
Hi, thank you for your talk. So just to get back a little bit to the Utopia, I know we've spent a lot of time on it, so feel free to skip over if you want. But just curious, without going into the technical details, like, can we say anything about, is it possible to even know, like, given an arbitrary step, like, how would you even know that, yes, this is getting us towards that better world with only sample access from the real world? And then just really brief question to state, I don't know if you want to answer this either, but I was wondering when you talked about probability and sort of what it means, it kind of reminded me of like frequentism versus, you could take a totally different approach to probability and say it has nothing to do with frequencies. Have you thought, I assume you've thought a lot about that, and could you give us any like hint from what that perspective might offer?
Yeah.
Thanks.
So let me answer the second question first. I would like to refer you to a paper by Philip David called On Individual Risk, where he basically talks about this question, looking at it through, I think, maybe 7 different definitions of probability, and not necessarily reaching happy conclusions in any case, in any one of them, but he knows a whole lot more about that sort of thing than I do, and I think it's an excellent reference on individual risk. Yeah. Remind me, what was the first part of the question?
Just like how we can hope to study based on real life samples.
I think that, so, we have this initial result about towards a better world. I think that the next step is literally to, I think similar to the question that was asked over here, to start thinking about what you would like to put in there and see whether the transformation can satisfy the condition. And I think it's going to be, we need to play with it a bit, or anybody, play with it a bit and try to see how that can develop. It's very recent.
Okay, I think we have one last question in the front.
Thank you. Very fascinating and interesting. And I would like to continue maybe connecting to the potential practical ramifications and implications. And maybe if we connect it to social scientific perspective and look at theories like those of social capital, and we go popularized by Putnam in the 80s, where we can see connectors between societies of high levels of relational interconnectedness and trust between people, and what we maybe would see more as an utopian society and less as an destructive society. Would you see ways of using these tools or models to give policymakers, civil society, entrepreneurs a framework or a map for creating solutions that can help us create more socially interconnected societies. Because the problem that we are seeing is that we are getting a more and more polarized public conversation, and with these echo chambers, and that is sort of making it really hard to build a democratic society. So can we use this in any way to counter that?
So I can think of a few different settings in which I have reason for optimism. Okay. Like you mentioned, I don't know, the filter bubble sort of things, right? So I think that if you can frame the better world as encouraging, like trying to figure out what kind of cross-filter bubble communications have some possibility of being read on the other side or landing on the other side. I think that can be formalized. I think it's a totally reasonable goal, and I think it is in a better direction. It does take us toward a better world. There are other examples that also come to mind, but I think that's the simplest one. So I am optimistic. And again, just like the questions from the last row there, like think about what you would want to do and see whether the technology can apply.
Thank you. Thank you. Let's give a last round of applause.
Thank you.